Hello, my name is Andrew David Hazy, and I'm a retired instructor from the Rochester Institute of Technology, where I taught technical, scientific, industrial photography for about 45 years. I've been retired now for about 10. So it was a privilege to work at RIT in that area. I was, I think, about the only instructor that dealt in the subjects that I dealt with. The overall topic of scientific and technical photography simply, in my mind, raises the reality that photography has been an indispensable tool of science, engineering, technology, whatever, and society would not be where it is today had it not been invented at the time that it was. We all know about photojournalism, portrait photography, nature photography, and so on. But technical photography has a special niche in image making, and that is that it can add the possibility or the power of visualization of events that are normally invisible to the eye, or it provides the capability of making measurements of subjects, such as how fast they move, how long they last, and so on. So it's a tool for quantitative results as well as qualitative results. Why might events be invisible to the eye? I call them unseen by the naked eye. Because they might occur too fast, too slow, they're in a region of the spectrum that we can't see. It could be too far, too small. It could be in a hazardous environment, underwater, etc. But the two things that make photography so valuable is these two factors. Visualization of invisible events, or hard to see events, and quantification of those events as well. Now, I will today deal in high-speed photography. Not that I expect anybody to include these in a curriculum, but maybe the ideas that are generated might be useful in some kind of a independent study or personal project. So, high-speed photography. It implies, however, in spite of the fact that it's high speed, it implies that we're going to make photographs of these events so that they faithfully reproduce the condition of a subject at a particular time. This implies that we make sharp photographs of fast-moving events. There are two concerns that we need to deal with. One of them is how to make it look sharp if it's moving so fast. Well, there's a way to determine that. It all comes down to a matter of ratios. The ratio between the amount of blur that we can tolerate and the size or time of the event that we're photographing. So, for example, if an event lasts 10 seconds and we make an exposure of 1 second, in that case the amount of blur will be equal to 1/10 of the size or time of the real object. And this is how we can make sharper and sharper photographs, by making the time that we look at the subject for shorter and shorter. So that's how you choose an exposure time, if you know something about your subject. If you don't know anything, well, then just do anything and then look at the results and decide later. But the other factor is that if an event is high speed, it's there for a very short time. So it is important to make sure that the camera or some other device operates at that exact time. So synchronization becomes a major problem when an event is there only for a millisecond. Okay. So how do we solve these two requirements? Well, we're not going to use cameras to make make a photograph other than to record light. You'll see what I mean by that in just a minute. Operating a camera is very difficult. The cameras are slow in reaction time. So we have an event that's very short in time, making sure the camera operates at that time is quite difficult. So we need a fast-acting shutter, so to speak. It turns out that it's a lot easier to turn a light on and off than it is to open and close a shutter. So what is this light all about? Well, it's an electronic flash. An electronic flash was popularized, devised, and characterized by Harold Edgerton at MIT in the early 30s. And now stroboscopes and flashes like this are available all over the place. This is a very basic, popular flash. It only costs, I think, about $45. Unfortunately, it comes from China, but take it or leave it. So what we're going to think about is how to make this flash to capture a high-speed event. Well, we're going to use a synchronizer. Well, here's a synchronizer. It consists of two copper-clad plates. The copper is facing The copper is facing each other on the plates, and they each have a wire attached to them, and we're going to connect two clips to it, to the wires, and the household plug is going to plug into a readily available extension that is used for electronic flash triggering. It has a household socket on one side and a PC, whatever that is, connector on the other side. This plugs in on the other side. This plugs into the flash synchronization cord. The other end goes into the household plug or socket, and then with the two clips go to the two plates that are separated by a very small amount. So now we want to take a look at what the impact of this box looks like at the time that it hits that plate. And what we want to do is use the plate itself to close a circuit that makes the flash fire. So we're not going to actually make a picture of it. You'll see the process. There you go. It hit, and you could add a cup there, water splashing out, and so on. It's one way. So there are other approaches that we can take, and in this case it's a very simple one, and it's based on using clothespin that has thumbtacks pushed through the two ends, and so the clothespin keeps them together. Each one of them Each one of them, the thumbtacks has a wire attached to it, separated, and what we do is we place a piece of paper, cardboard, whatever, in between the two. So now they're separated. And we take the two wire connections and connect them to the two wires, which are now not connected, right? Because the piece of paper is separating the two thumbtacks. Now we take the synchronization paper, and what we're going to do is pull it out. When we pull it out, they come together, flash goes off. And over here you could put a piece of string, attach it to something that's moving or falling, and you choose the spring, the length of the string, so it's just long enough to undo the connection over here, or make the connection at the time that you want it to, either a little earlier or a little after, don't work, but a little earlier than it's supposed to. So, and this is what it would look like when the paper is pulled out. Okay, so synchronizer, mechanical synchronizer. It's useful in some situations. But in our case, we're going to be photographing something which is a little different than what can be done with those synchronizers, or could be done maybe easier. We're going to set off the flash by an acoustic trigger. The acoustic trigger in this case is going to be based on the use of a fairly inexpensive cassette tape recorder or other type of an amplifying system that has a microphone out jack. Now I need to set up the props for this, and I'll be back in a second. As when I just left off, I mentioned that I was going to get some props, and I did that, and here I am back, and we're going to be looking at a high-speed event, and we would like to do a couple of things. One of them is to visualize what's happening in this event. And what's the event? Well, a balloon. And the high-speed part of it is going to happen when? When it breaks. And what's the visualization part of this have to do with anything? We want to see what a hole looks like in a bursting balloon. Normally you don't get to see those because they happen too quickly. So in our case, the balloon is going to explode. I'm going to use an X-Acto knife to blow it up. And we're not going to use a mechanical synchronizer, but an acoustic one. And that is based on the use of a cassette tape recorder. And the cassette tape recorder has two, one is an output, one is an input, having to do with sound. The input is the microphone, the output is the earphone, and that output puts out electricity when the tape recorder hears a sound, so you can monitor the sound. That can be used to trigger a silicon control rectifier, which I have in this little plastic embedded little can. The device itself costs maybe 75 cents, maybe less. Silicon control rectifier. And this will close a switch when electricity is fed to the base. So I have a smaller one in the tape recorder right now, but you can see what this would look like, or what it would do when it's in operation. So the earphone is connected to the SCR. That's connected to the synchronization cord of the flash. And now I'm going to turn the tape recorder on. And what happens is that it's so sensitive that it's hearing my voice. Let me turn it off for a second so we can talk. So at the time that the photograph will be made, the lights will have to be out, because if you open the shutter now, waiting for me to break the balloon and so on, room light is going to expose the scene. I'm not going to do it in the dark, but you will see the results a little bit later on of what the image looks like. So we'll do it in room light, and then we'll look at a typical result. So we'll put the tape recorder right there. And I will not say anything before I do this, because I will trip the flash. So imagine the room lights are going out. Can't see anything. And we'll turn the tape recorder on, and after that, sometime I will pop the balloon. Okay. A little bit more inquisitive. Here's another balloon. What we want to do is to find out roughly how long it takes a balloon to disappear, from the time that it's punctured until it's pretty much gone. How are we going to do that? Well, we could use a very expensive high-speed camera and so on, a motion picture camera. We're going to do it using a little bit of intuition and some knowledge about physics. So we need to photograph the balloon later. How do we do that? Well, obviously, we move the microphone about a foot away from where it was before, right? Now it's going to take sound a little more time to go from here to there. A little more, a foot. And what's that foot stand for in terms of time? Well, I like to remind audiences that in elementary school, probably the teacher at one time mentioned that you can determine how far lightning is, or struck, by listening to the thunder. So if you see lightning, you start counting. If you count to 5, it's a mile away. Well, how far is a mile? Roughly 5,000 feet. So in 5 seconds, it goes 5,000 feet. In 1,000th of a second, it'll go 1 foot, right? I think so. So this next photograph will be delayed from the first one by 1,000th of a second. Let's see how we do that. Well, we're going to do the same procedure. Lights out. Eventually we open the camera shutter, and then we break the balloon. And if I make any noise, of course, it's going to go off. But ignore that. Okay. So we take a look at the two photographs. One of them has a rip in it that's some size, and I would ask an audience member to tell me, how much of the balloon do you think has disappeared? Well, the answer, I gave it to them. A quarter of the balloon has gone. So then we look at the next photograph. Obviously shows a balloon more broken than the first one. And I ask the same question. Well, sort of the same question. How much of the balloon remains? Well, the answer, I give it to them, is a quarter. It may be a quarter, it may not be. Let's not quibble. The idea is that it may not be. Let's not quibble. The idea is the thought behind it. It could be 3/8. It's just as easy to, go for the easy answer. Yes. So a quarter has gone. A quarter remains. How much of a change in the balloon was there between the two? Well, a half. So if a half of the balloon disappeared in 1,000th of a second, how long will it take the whole balloon to disappear? A 500th of a second. So we learned something about the performance of a balloon, the lifetime of a breaking balloon, by using some previous knowledge and manipulating time. And I hope you found this interesting. And thank you. Hello, my name is Andrew David Hazy, and I taught technical and scientific photography at RIT for many years, and now I'm trying to share some of the concepts associated with the items that I used to teach for those many years. Although I've decided to approach this from a very basic point of view. I've had to do that for years myself because the budgets never really supported full-fledged involvement in those topics. I prefer to think about this instead of just technical photography as applied photography, photography that is used to examine and record and measure events that are difficult to see under most photographic conditions. I mean, we normally think about photography as maybe photojournalism, nature photography, sports photography, wedding photography, and so on. Those generally just record events as they happen, as we normally see them. But in my case, I was interested in photographing and looking at things that are difficult to see, just because it's interesting to do that. So, what are things that are difficult or unusual to see? Well, one of a very simple thing to think about is making a photograph of a ping pong ball. Anybody can make a photograph of a ping pong ball. You light it this way, light it that way, photograph it from any angle you want, put it into props and so on. So you end up with a picture of the ping pong ball that looks like a ping pong ball. But if you want to do a little bit more than that, in that case, one of the earliest things or first things that I would think about is, for example, making an illustration for an annual report that is the ping pong ball, but in a different light. So instead of my concern in the past has been in making sharp photographs of events or of fast-moving events. In this case, what I'd like to show you is what you can do to expand the range of possibilities for illustrations associated with a ping pong ball. So instead of making a sharp photograph, what I would suggest is that you might want to make a blurry photograph. Now, how do we do that? Well, let's see. This is one way we could do it. That would make a photograph that's different from most others, and that is to just simply make the ball bounce along the table and then take a look at the resulting photograph. All the time that the ball is bouncing, the camera shutter is open. Obviously, you have to take some care in terms of the background that you use, and the best thing to do, because the background is exposed all the time, the ball is only exposed as it travels a distance equal to its own length, so it bounces along. But what can we tell from the photograph that we just made? And here it is. Well, now that you've seen it, one of the things that becomes obvious is that we can tell that the ball bounced lower with each bounce. And we can also tell that how much of a height it lost from bounce to bounce. That is, if we had included a scale, right? So including a scale in most photographs that you're going to be making measurements from is important. Luckily, we have a built-in scale in the photograph. You normally don't think about this, but in fact, the subject itself, the ping pong ball, provides scale. It is 40 millimeters in diameter. It's a standard. So we can use the diameter of the ping pong ball to estimate how much height there was lost between each bounce. It might be two ping pong balls worth from one to the other, and less and so on. But if you're really inquisitive and realize that you can also tell something else, in that case, what I'd like you to do is take a look at the trace again. You'll notice that the path of the ping pong ball is not uniform in brightness or density. And on its downslope, it picks up speed. Actually, it picks up, and then on the up slope, it loses it. So the brightness of that trace actually is an indication of how fast the ball is traveling. And with a little bit of ingenuity, you can assign a speed to a particular density. That's not easy to do, but it's a problem that could be solved, or might be solved, with a little bit of curiosity and perseverance. So, what else might you approach in this particular fashion? Well, one of those things is the flight of, and this is a project that I've used myself in class, is the flight of a maple seed falling down, or one of these little whirligigs. Oops, there we go. So you might be interested in finding out what the rotational speed of this, or the terminal speed of this, some of them cooperate and others don't quite so well. There we go. If you wanted to find out how fast those seeds turn and what their terminal velocity is, in that case you could approach it the same way as you did with the ping pong ball. You essentially drop it, and as it's spinning, you make a short exposure, and that leaves a blur. And then you take a look at the result, and you make an analysis from that. In this case, again, you don't want to make a sharp photograph. You want to make a blurry photograph. The blurry photograph gives you more information than a sharp one, because in a way it includes time. So we're going to make an exposure of 1/5 of a second, and we'll drop the seed, expose it for 1/5 of a second, and then we'll take a look at the result. And again, this is what it looks like once you have made it. And this is the first, that was the first instance, but now I'm going to add some information or caption to it. Now from this we can tell, as you saw, we can tell two things. By counting the spikes on that rotating seed, we count 5 of them, and the exposure time was 1/5 of a second. So the rotation rate is 25 rotations per second. And as far as how far it's falling, again, we need a scale. Well, the scale is provided by the included ping pong ball that I placed in the scene. We know that ping pong ball is 40 millimeters. We measured it, and it's a standard distance. So then we measure the length of the blur in terms of ping pong ball diameters. And it turns out that 160 millimeters, and it traveled, because that's 4 ping pong ball widths, and the ping pong ball is included in the picture, at the same distance as the falling seed was. So 160 millimeters in 1/5 of a second, and that turns out to be 800 millimeters per second. So we have learned not only how fast that little whirligig turns, but also how fast it falls. And here you can see one where the seed changed speed. But we can do more. We can do more in terms of looking at a ping pong ball. So what was missing in the blurry trace of the ping pong ball as it bounced across the table? Time. We know the total time. Maybe actually we don't even know that because we missed the beginning and the end of the trace. But that's not important. What we need is time. How do we get time included in a picture like that? Well, one of the ways is to use a stroboscope. A stroboscope, normally we think about a stroboscope as a flashing light. Well, I'll show you. Here's a flashing light. This is, again, a fairly inexpensive electronic flash. It's, I think it's in the area of $50 or so. And when you operate this, it produces either a single flash or it can produce a series of flashes. And I think we're going to go here. And that's 40 flashes. 40 flashes at 20 flashes per second. And the result of lighting the bouncing ping pong ball with a stroboscope is that we produce a photograph where there are individual images of the ping pong ball separated by a 20th of a second each. So now we can determine how fast the ball is traveling at any given position along the curves. So not only we know what the height change is, but also we know the rate of motion. The stroboscope, even though it's only $50, it has some limitations. However, I've looked at another type of a stroboscope, a mechanical stroboscope, and that's simply a disc of paper with a slot cut in it, and it has a little motor at the back, and that can be spun, and each time the slot goes past the opening where the camera is attached, there's one picture of the ping pong ball made. And we're going to rotate this 20 times a second, same as the stroboscope was running. So in this case, I'm going to, the strobe is already, the mechanical stroboscope is already attached to the camera, and so I'll start it running. You can hear it now. And I will close it, and then close the shutter, and then we take a look at the result. And as you can see, the result is very similar to what we achieved with the stroboscope, which we would have operated. Which would have operated exactly the same way. What we would do is drop the ball, and as it's bouncing along, we operate the flash, and we end up with a sequence of photographs. The two are very alike. The difference is that this little mechanical strobe is probably costs $5, and this one costs $50. The limitation with this is that you're limited to 40 flashes at a time, whereas the other one has no limitation. And anyway, it's an interesting gadget to build and to experiment with without investing in that much money. And this, making one of these, is very well within the skill level of just about any student. The first time that I made one of these was when a middle school student asked me for some guidance on stroboscopes, and I suggested something like this, and she won a science fair prize with it. So one thing remains, and that is to find out how fast the mechanical stroboscope is turning, so that we can make sure that it's flashing or exposing 20 times a second. We need to calibrate it or measure it. Well, how do we do that? We can rely on the accuracy of our exposure time on a camera shutter. So what we do is to choose a some shutter speed, and I'll choose a half a second. And then we will make a photograph, not by just dropping the ball and keeping the shutter open all the time, but as the ball is moving, we will make an exposure of 1/2 of a second. And so we'll turn on the stroboscope again, and this time, while it's bouncing, I'll make an exposure. So here's turning, make a 1/2 a second exposure, and then stop, and we'll take a look at the result. And the result, as you can see, is a number of images of the ball in different positions. And those are made during a 1/2 a second exposure. Well, if we count the number of images of the balls, we find that there's 10 of them. Well, if there's 10 in a 1/2 a second, there'll be 20 in a full second. So the stroboscope, in fact, is turning at roughly 20 revolutions per second. And that gives us timing information just as much as the electronic stroboscope had already been calibrated to flash 20 times a second. This one makes images at 20 times a second, which we can then use to measure things. So we have used a very simple approach to measuring the rotational speed of the strobe and making it useful. Hopefully, this little segment has been of use to you, and if you have any questions that you would like or that you'd like to discuss, feel free to contact me by email, or I guess that's the easiest way. There are also some articles referring to this topic in the resources page associated with the presentation in the technology conference. So thanks a lot for listening, and I hope that it's been a little bit of interesting. Thank you very much.